about another flux that you can calculate with our framework for the far zone that also turns out to be very important, not so much for detection of gravitational waves, but for astrophysical reasons. And that's the flux of momentum. So as I pointed out, you have gravitational waves that carry energy. But those waves are a null field, right? It's like a photon. Photon carries energy and momentum, and the momentum is equal to the energy, with a factor of c in there somewhere, times the unit vector along which the photon is propagating. In exactly the same way, gravitational waves carry energy and momentum. And so you can calculate the momentum flux by a very simple rule. I mean, you could calculate it from our rule for our formula for Pj, take the time derivative. But just by thinking about it for a second, it's clear that the rate of change of momentum, the flux of momentum at infinity, the rate of change of momentum is equal to this thing which gives you the flux in a given direction of energy, and just multiply by the unit vector. It gives the direction of that flux. And then average overall directions and see if there's a net momentum radiated in one direction or another. And there's a factor of c in here to make all the units come out. Okay, so you just plug in the formulas that we had before with various unit vectors. One thing, of course, you'll notice right away, if you've sort of looked at what we did for energy, this formula tends to have all even unit vectors, either 0, 2, or 4. Okay? So, but there's an extra n here now, so you might say, well, there's surely no momentum flux, because what's the value when you integrate an odd number of unit vectors around a sphere? 0, right? But what it means is that when you look at the contributions to h plus and h cross, you have to include some of the higher multiple moments. The quadrupole moment itself doesn't emit any momentum, but the next moments do contribute to a momentum flux. So it turns out after you do all this averaging, and then for the next highest moments, you now get an extra n, and so you can get an even number. So the final formula after you do all the angular averages is that the momentum flux is 3 time derivatives of the quadrupole moment times 4 time derivatives of the octupole moment. Okay? And of course, you had to have something higher because you need a free index j, because p has an index j. So we needed some extra index somewhere. So PQ get contracted, but this j is free. So it's a product of these terms, but notice it involves a higher order multipole moment, an octupole moment. And furthermore, there's even a term that comes from, there's the standard quadrupole moment, 3 time derivatives, and this is the current quadrupole moment. The quadrupole moment generated by the momentum current, T tau 0j. So these higher order moments you have to include, but when you do it, you get this nice answer. And then for a binary system, this is the result. Delta here is the difference between the two masses over the total mass. Eta is, again, our symmetric mass ratio, and usual factors, gm over c squared r to the 4th power, and then a bit parallel to the velocity of the particle, the orbital velocity, and another bit in the radial direction, but multiplied by r dot. So that's the formula for the energy, the momentum flux from a binary system. Notice it depends on the mass difference. If you have a system of equal masses, there's no momentum flux. Again, it's the same sort of argument as we've used in other cases. If you have 2 equal mass particles and they're emitting gravitational radiation, which way is the flux going to go? There's no preferred direction. You know, it's not up or down, because up is the same as down. This way is the same as that way, because you have equal masses. And so symmetry in that case tells you there's no momentum flux. So it depends on the mass difference. So you have to have an asymmetric binary to get this momentum flux. And what happens with this momentum flux is that, notice and let's simplify things to a circular orbit to make life simple. So this term goes away, r dot is 0. This is 0, b squared is just gm over r. It's a simple formula with just this velocity j. So this says that the momentum, the rate of change of the system's momentum, of course, it's opposite to the momentum flux. So, and it's in the direction, the acceleration of the center of mass is in the direction of the velocity. So the center of mass wants to go this way, but of course then the velocity changes direction, so the center of mass wants to go this way, and then it changes direction again. As the orbit goes on, the center of mass goes around its original point. As the orbit inspirals, because we're also losing energy, so r gets smaller, so the effect gets bigger, so the system moves around its center of mass on a bigger and bigger spiral. Okay? So this is the center of mass of the two-body system. It spirals outwards, and it just keeps going until the gravitational radiation turns off. And that will occur, typically speaking, in an in-spiraling binary when the two bodies merge to form the black hole, because then there's no more flux of gravitational radiation, and so there's no more momentum recoil, and so the velocity that the system gets is simply the velocity that it had when gravity waves stopped. And then it just continues uniformly in that direction with that speed. Right? Okay, so I've said all that. Oh, one interesting thing, and this was a suggestion made by my student Alan Wiseman, is to note that the recoil of the system, if you just stare at this formula, and carefully remember this is V1 minus V2, and this delta is M1 minus M2, and so on, that the recoil velocity, which you get by, first you have to integrate this once to get the momentum itself, or the velocity. The recoil velocity is opposite to the velocity of the lightest particle. So in other words, if the lightest of the two particles is moving this way, then the recoil of the system is opposite. And he made this following analogy. I don't think it's a perfect analogy, but I thought it was pretty cute. In electrodynamics, if you had two charges going around like this charge, of course, is moving faster than the heavier charge. And you know when you have a charge that's moving fast, the electromagnetic radiation is beamed in the forward direction. Right? This is the relativistic beaming in electrodynamics. So by analogy, he argued that the lighter mass, since it's moving a little faster, it's emitting radiation, but that radiation is beamed in this direction, whereas this more slowly moving massive guy, its radiation is much more isotropic, it's not beamed. Well, if this is emitting more radiation preferentially in this direction, then there's momentum going in this direction, and therefore the system must recoil in that direction. Oops. It's not a perfect analogy, I think, because of the difference between quadrupole gravitational radiation and dipole electromagnetic radiation, but I think it certainly fits the formula that the recoil is always in the direction opposite to the motion of the lighter moving body. But I think it's kind of a cute analogy that gives you a sense of it's this anisotropic emission of radiation that's responsible for the recoil. Well, it turns out this is a very important effect, not so much for gravity wave detection, but for astrophysics. And it actually has an old history. Already back in the 60s, various people pointed out that this momentum flux involves the interference between the quadrupole moment and the higher ones. And we see that. It's the quadrupole here coupled with the higher octupole moment or with a current moment that is responsible for this effect. It was first calculated for binary systems by Fitchett and Detweiler in the 80s. My student Alan Wiseman calculated the post-Newtonian correction to that formula, and later Blanchet, Kusaila, and I calculated the 2PN correction to that formula. But what it would mean is, for example, if you had two black holes in the center of a galaxy that merge together to form one, and this we believe is common in the centers of galaxies, especially ones where two galaxies have merged to form one, then, for example, if the final black hole has enough of a kick to be ejected from the galaxy entirely, then that would affect the merger rate of future mergers of galaxies. I mean, we believe these supermassive black holes may form because two galaxies, each with a black hole, merge, the two black holes find each other, merge, and then you have a bigger one. Then another merger, you get a bigger black hole because two black holes have merged. But if that merger causes this black hole to be kicked out of the galaxy and then to move through intergalactic space, you've lost a black hole that could merge with something else. And so Jeremy Schnittman pointed out that that could have an impact on these kind of growth trees that people use to try to predict how supermassive black holes might form. If you have one of these mergers in a dwarf galaxy or a globular cluster, which have a rather flat potential well, then if you get enough of a kick velocity, it could exceed the escape velocity from that system, and then these things might not have as many central black holes as you thought. And finally, even if the kick that the final black hole gets is not enough to eject it from the galaxy, so if it stays there, it's then the galactic potential will make it just come back, and it'll move around the center of the galaxy. Well, that motion of a black hole in amongst the stars and gas and dust that are there could have interesting effects on the nature of the galactic core. And a lot of these effects were pointed out in a famous paper by David Merritt, Milosevic, Pavada, Scott Hughes, and Daniel Holtz, in two papers, one pointing out summarizing the theory, and the other pointing out the various astrophysical consequences. And in fact, there was an observation, I'm not sure how solid, how that one is, the observation is still holding up, but there was a tantalizing observation by Comosa et al. Of a black hole in the center of the galaxy. The black hole had an accretion disk, a supermassive black hole, but from looking at the spectra of light from the accretion disk, they found that this black hole was moving at 2,600 kilometers per second relative to the galaxy itself. So they suggested this might have been an example of a black hole that got kicked from the earlier merger. And so this turned out then to be a rather important effect that people really wanted to study and began to study seriously. It was also an important observation, a very influential paper for another reason, because it generated some really bad titles for papers. The first one, that original paper, was How Black Holes Get Their Kicks. This was followed a short time later by a numerical relativity paper calculating the kick using numerical relativity, getting a kick out of numerical relativity by Joan Centrella and her collaborators. And then, this was a famous one, Total Recoil, the maximum kick from blah, blah, blah. That's not Gabby Gonzalez, that's a different Gonzalez. I heard a rumor that they had asked Arnold Schwarzenegger to be a co-author on this paper, but he refused. And I'm just waiting for the day when we see this title, A Swift Kick in the Astrophysical Compact Object by Boot, Foot, et al. I haven't seen that one yet. But still, astrophysically, it's a very interesting phenomenon. And so let me just illustrate another application of post-Newtonian theory. What Blanchet and Kusaya and I did was to try to calculate this effect using post-Newtonian theory, because we determined the formula for the flux to second post-Newtonian order. So the result for the kick depends on the reduced mass parameter. When n is eta is a quarter, that's the equal mass limit, so the kick has to go to 0 by symmetry. And when eta goes to 0, that just means one of the bodies has negligible mass compared to the other, and also you get no kick, because you get essentially no gravitational radiation when this is a test body. So at the two ends, of course, you have to get nothing, and then you get some kick. And we actually studied a little bit how, at various levels of approximations, how the numbers went, just to see if these numbers converged in some way. And we found actually, including the 1.5 and the 2pn, you got sort of agreement. So it suggested that you could get some decent predictions with this method. And we estimated some kind of error bars. And notice the maximum kick here for a specific mass ratio, and the kick is a maximum, it was around 250 kilometers per second. But then in the, oh, right, 250 with this is the mass ratio, m1 over m2. With a 1/10 mass ratio, you get about 70 kilometers per second for the kick. But soon after this breakthrough in numerical relativity that allowed people to really do numerical simulations of binary black hole mergers, the team at Goddard Space Flight Center, headed by John Baker, did a calculation of the kick that you would get if you, sorry. What are these? Oh, up to the, this one. So here we carried the calculation only up to the innermost stable orbit, which is the, it's this one. Why does it go, why does it go to 0 there? Oh. Oh, so because what we did was found what we thought was a clever way to do the integration effectively beyond the ISCO. It's one of these ways of trying to push the post-Newtonian approximation a little bit beyond where you think it's valid. And it turned out that by integrating not with respect to time or with respect to separation, but by integrating with respect to a certain redshifted orbital frequency, the higher order terms turned out to be, in that re-expansion, smaller than the lower order terms. And so by integrating with this little trick, that took us beyond the innermost stable orbit, we got this result, which agreed with the 1.5 PN result. And so it was just a way of trying to get the best accuracy we could from these calculations. So this is one where we just truncated it so early that you don't get the maximum effect. You remember the kick all comes from the very end, right? You know, it's this thing. So it depends on where you stop the calculation. If you stop it here, you get this kick. But if you keep going, you'll get a bigger kick. You know, so it really depends. It's sensitive to where you end the calculation. And for these curves, we found what we hoped was a trick to push the calculation further in than maybe we were justified. Right? Yeah. So these we got by sort of varying where we ended the terminated the calculation to see the range. And what else did we do? Yeah, and it was really just varying the range of the endpoint that gave these kinds of error bars. Again, this is not experimental physics. These were just, you know, being safe, giving us some wiggle room in the calculation. Because again, this is an approximation, and unless you know what the errors are, the higher order terms, you don't quite know how accurate your estimate is. And we certainly did not know the 3PN terms at that time. But to give an illustration of the accuracy of this post-Newtonian calculation, here's a calculation of the kick produced during from a numerical relativity simulation. And these are actually 3 different simulations with a different with different resolutions in the computer code, just to illustrate that they could really get real values that were sort of convergent, depending on the grid resolution. And you see the velocity is very low, but then as the in-spiral goes, and they get closer and closer together, it increases. And this is about the innermost stable orbit, about the place where we cut off our calculation. And the value we got for this particular mass ratio agreed pretty well with what they had for that numerical simulation. But it turned out that after this peak of the kick, there was an anti-kick. Some gravitational waves are emitted in the opposite direction to reduce the amount of the kick. There's been a bit of a story as to what is responsible for this anti-kick to bring the value back down to about 100 kilometers per second. It probably has something to do with the quasi-normal mode radiation that the final black hole emits. It's a bit asymmetrical, and maybe it just always emits a bit in the opposite direction. There are some other theories for why this happens. But at least up to the point where we think the post-Newtonian theory works reasonably well, we agreed reasonably well with numerical relativity. This phase of it really has to do with the real merger part or the ring down part. You cannot analyze with post-Newtonian theory, and so, you know, we accept that. But I think it's sort of, I view it as another example of this effectiveness of post-Newtonian theory at deriving useful things, even in a regime where post-Newtonian theory is getting a bit shaky. Okay, the final thing I want to talk about is the radiation reaction. As I've said before, when the system emits things like energy, momentum, angular momentum, the flux that's carried to infinity has to be balanced by a loss of those quantities within the system itself. Now, you could simply assert that as a fact. If there's energy flowing, then the system must lose energy. But how does it lose energy? Well, to lose energy, there must be forces within the system that are linked to the waves that are going outward in some way. And those forces within the system must then be responsible for the damping of the orbit according to, in a way that agrees with the quantities that are radiated to infinity. So for example, there must be within the system some kind of force, a radiation reaction force, such that if you take the force, dot it into V and sum over the bodies or integrate over the system, you'll get the energy flux, dE dt, or the energy loss. So what is this force and how do you get it? Well, you can get it from this post-Newtonian theory. But to find it, remember I talked about the fact that energy loss is of order c to the minus 5. It's a 2.5 post-Newtonian effect. So that means you have to find the near zone fields in order to get this force and calculate them up to 2.5 post-Newtonian order. 1 PN order is not enough. 2 PN is not enough. You have to go to 2.5 to get the leading terms. But you can do it. We return to our near zone calculations. You have to iterate the relaxed Einstein equations 3 times. So you start with 0 on the right-hand side, calculate H1. Plug that into the right-hand side, calculate H2. Plug that back into the right-hand side and calculate H3. You have to do it 3 times to get all the relevant terms that you need for this order. And that gives you the metric to 2.5 post-Newtonian order. Plug that into the equations of motion for the fluid. And then you get your equations of motion. And then in these equations, say the hydrodynamic equations, there are Newtonian, 1 PN, 2 PN, 2.5 PN, etc. terms. Notice there's never a 1.5 PN term. We argue that that term never appears. First odd or half-order term appears at 2.5. Now you might say this is a lot of work. You have to calculate 1 and then 2 and then 2.5. It turns out that just to get the leading 2.5 PN terms, you can skip the 2 PN. It's this idea that, skip going from odd to even. They tend to occur in very different classes of the calculation. So you can skip 2 PN and go directly to 2.5 and calculate those terms easily without knowing anything about these terms. You do know that they conserve energy. And so it's really this that you care about. That's what's going to make the energy decrease. But on the other hand, all this work has been done. So we know the 2 PN terms explicitly. We know the 3 PN terms. We know the 3.5 PN terms and on and on. But if you just, as students, want to do the calculation, you can go all the way to 2.5 PN and work out those terms without worrying about this mess. And this is what we do in Poisson and Will. We do that. We skip that and just go directly to that. And again, let me remind you of what we talked about before, how this might work. So here's H00, for example. And to lowest order, the gradient of that is going to be contribute to the acceleration of any particle. So there's our Newtonian part. But keep in mind, we've iterated 3 times. So H gets solved for high order, and H appears inside there. Remember, tau contains the H field in many places, within the matter stress energy pseudotensor, within the Landau-Lifshitz pseudotensor, etc. So this will inside contain 2.5 PN terms. There's no half PN term. We saw that before because of the conservation of mass or energy to this order. There's the 1 PN correction term, and there could be some corrections there that might contribute at 2.5 order. Here's the 1.5 PN term that at lowest order doesn't contribute, but it can make a contribution at 2.5 PN order, so you have to look at that carefully. You can't just throw it away blithely. You have to look at it carefully. There's the 2 PN term, but we don't care about this term, so you can throw it away. Don't worry about it. It's 2 PN. There's no 2.5 PN contribution there, and you can show that. And then we have this one that we said was a 2.5 PN contribution, 1 over c to the 5 time derivatives, and then we saw that this looked something like, it looked like this involved the quadrupole moment. of the source after we expand it out x minus x prime. So I'm not going to give all the details. It would just fill a view graph for what the final answer looks like, but I'll just show it schematically. So for the Eulerian equation of hydrodynamics, you get rho star dv dt, you get Euler's equations, you get post-Newtonian corrections that we've already seen, you get 2pn corrections, which we're not bothering to calculate, but you could, and then you get this radiation reaction force. If you're dealing with a system of just small bodies or point masses, then the force on each body, body A, is simply the integral of rho star times the acceleration, so it's rho star times this f d3x. If you're dealing with a two-body system, then you do this for body 1, for body 2, take the difference in acceleration between the two, and then you get the relative acceleration between the two bodies. And there's the answer for the 2.5 pn acceleration. So notice it's 1 over c to the fifth. That's the signal that is 2.5. Notice that it's odd in velocities. There's a v squared and a r dot, gm over r and r dot. Odd. If you let t go to minus t, v changes sign. Again, this is the indication that this is a dissipative process, not a conservative process. And so this then will cause dissipation in the orbit. Okay, now we've derived this directly from our post-Minkowskian approach, right? We derived h's, all the h's, we plugged them in, we did 3 iterations, blah, 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 blah. The question is, does this give the same energy flux as we got when we calculated the fields at infinity? Okay. We need to check that to be sure. And this was done in our harmonic gauge, and so this has a specific form, but remember, the coordinates are not unique. We could change coordinates if we wish. This particular formula is also sometimes called Damour-Deruel gauge, after Thibaut Damour and Nathalie Deruel, who first worked out this particular formula for the radiation reaction in a two-body system. But there are other gauges. You can change your coordinates to make that radiation reaction term look a little different. And there's another gauge, actually, today it's called the Burke-Thorne gauge, after Kip Thorne and his student Bill Burke back in the 60s, where you change the coordinates in a clever way so that all the radiation reaction forces are embedded into a new Newtonian gravitational potential. So the new potential is equal to the standard Newtonian potential plus a 2.5 post-Newtonian correction term that involves 5 time derivatives of the quadrupole moment. This is the STF part of the quadrupole moment times xj, xk. Okay. It's a very nice form because you can basically use Newtonian theory as long as you don't care about post-Newtonian or 2pn effects. If you just care about the radiation reaction effects, you just take Newton's equations and plug in this new potential, and this will give the radiation reaction effects. So it's a quadratic in the position, so when you take the gradient, you get a force that's linear in the separation, and it involves 5 time derivatives of that object. So when you do that for a two-body system, you get a formula that looks a little different from the earlier one, but again, it's simply because you're in a different coordinate system. But now, suppose you take that formula and calculate, say, what's the rate of change of energy that this produces? And so for energy, the rate of change, since E is proportional to 1/2 v squared, then E dot is just v dot A. Okay? So if you dot that radiation reaction acceleration into V, oops, then you should get the rate of change of energy. Or if you want the rate of change of angular momentum, since J is x cross V, take the time derivative, that's just x cross A radiation reaction. So again, you should be able to do that and get the rate of change of angular momentum. And you can do a similar calculation for the momentum kick. And when you do that, plus some manipulations that I'll just illustrate on the next slide, when you do that, you get results for dE dt, dJ dt, and dP dt that agree completely with what you get from a calculation in the far zone using the energy fluxes. And you should really think of this as a pretty impressive result in the sense that you're taking two extremely different approximations, one, a multiple expansion in the far zone, integrating over the surface at infinity to calculate these fluxes. The other, a completely different expansion, expanding in powers of retardation, staying within the near zone, doing the calculation, but the answer you get for these quantities is exactly the same in both methods. So it really tells you that energy balance works. You don't have to just assume it. Energy goes to infinity, but the same amount of energy is lost by the system because of these internal dissipative forces from radiation reaction. And let me just illustrate this with one example. So here's, we take V dotted into our radiation reaction potential. This is for the Damour-Durell gauge. Okay, so dE dt is mu, the reduced mass, times V dot A, and there it is. That doesn't quite look like what we had over here. But then we have to appreciate that, once again, energy is not precisely defined. I mean, energy is only defined insofar as it's a constant, and even then, the zero of energy is not known exactly. You can add constant terms to energy, and you haven't changed anything. So it's really only a well-defined quantity when it's conserved. But when it's not conserved, you have the freedom to tweak the energy, the definition of energy a little bit, without changing the fundamental dynamics. And so it turns out, I think you can look at this particular combination of V squared R dot and R squared. If you take its time derivative, you get that expression. Here, just using the Newtonian equations of motion, because we're already at 2.5 pn order, we can clearly use Newton to manipulate these expressions. But you notice that this thing has a V to the fourth minus 3V squared R dot squared. Well, here we've got V to the fourth minus 3V dot squared R dot squared. So we can take these two terms and replace them with these two terms plus a total time derivative. And that total time derivative that you get can be pulled over to the other side into a redefinition of E into a quantity called E star. So it's the original E, the conserved E that you had before radiation reaction, plus a term that involves this V squared R dot over power of R, or over R squared. Okay? This is a 2.5 pn correction to the energy. So it's beyond 2 pn order, where we know energy is strictly conserved. So in a way, it doesn't really make a lot of difference. If we average over one orbit, it's not hard to argue that this averages to zero. These are just oscillatory functions. It's certainly zero for a circular orbit because R dot is zero. So there are many ways to argue that this is an irrelevant little addition, this higher order correction to E that's irrelevant. But in terms of this new E star then, having done that, these terms left over combined with those terms give you exactly the formula that we had before from the far zone flux. But to get that specific answer, then, you do have to do this sort of irrelevant redefinition of the energy by a 2.5 pn correction that you can insert. And the same holds for angular momentum and the linear momentum. The next thing you can do is to insert this radiation reaction acceleration, which was here. Take that acceleration and plug that into our Lagrange planetary equations to see how the orbital elements of a two-body system evolve with time. And again, you want to average over an orbit to see what are the long-term evolutions of those orbital elements. So you take that thing, You calculate the radial component, you calculate the tangential component. There's no W component, right? No component out of the plane, because this depends only on n and v. So the perturbation is only in the plane of the orbit. So the orbital plane will never change under radiation reaction. But when you do that, then you get an average over an orbit. You find that dp dt, the semilattice rectum, which is related to the semi-major axis this way, dp dt decreases. Again, it's order 1 over c to the 5th. With these factors that depend on eccentricity, the eccentricity decreases with some factors here. So the gravitational radiation makes a two-body orbit shrink, get smaller. A decreases. You can combine these to see that A, of course, also decreases. So that means the orbital period decreases, the orbital frequency increases. So you're starting to develop this chirp. But also the orbit circularizes. The eccentricity always decreases. In fact, you could show that if you just take the ratio of these two terms, you can get an equation for dp de. And if you assume that E is fairly small to start with, you can, that you can ignore these terms. Suppose E is 0.1 to start, then these are just tiny corrections to 1. So dp dt is just some numerical factor, dp de is just some numerical factor times p over E. This cancels, and you just get p over E. Eta cancels, you just get a numerical factor. So that allows you just to integrate E as a function of p. And the answer for that is that E over its initial value is of order P over its initial value to the power 19/12. Okay? 19/12 is just related to the ratio of these factors. Okay? But that says that as P shrinks, as the orbit shrinks, E tends to 0 faster than the orbit shrinks by a factor of a power of about 3/2. So P is going to 0, the orbit is shrinking to 0, at least for point masses. Ultimately, you'll get a finite black hole, but it's getting smaller and smaller and smaller, but E is getting smaller faster. So it turns out, for example, that for the Hulse-Taylor binary pulsar, and you can put in numbers, of course, going back to the dp dt, you can ask yourself, how long will it take for a given binary system with given initial conditions to reach a point where P is effectively 0? You can integrate then and see, especially in the circular limit, you can integrate, but you could also include eccentricity. You can ask, how long does it take before P is very, very, very small, effectively 0? And if you put in the numbers for various systems, you discover that the Hulse-Taylor binary pulsar will circularize and merge within 300 million years. And by the time it merges, by the time it's in its final many orbits, it's already highly circular with eccentricities of about 10 to the minus 6. So it really is in a quasi-circular orbit, that's just spiraling slowly inwards. The double pulsar, a system discovered more recently, which is a bit more relativistic, a shorter period, and so on, that will merge within 85 million years. And you say, that's an awfully long time. I mean, how could we? We're certainly not going to wait for that to occur in order to detect the gravitational waves from those in-spirals. But the important point is that those timescales are short compared to the age of the galaxy, or most galaxies, whose timescales are measured in gigayears. So it suggests that in a galaxy like the Milky Way, which is gigayears old, there should be mergers happening today, because there's plenty of time in the age of the galaxy for mergers that started out much, much earlier to be merging now. And so it's these kinds of arguments, the existence of things like the Hulse-Taylor binary pulsar and the double pulsar and their short merger timescales, that allow you to begin to predict rates of such events per galaxy like the Milky Way. And it's when those early estimates of rates were made, that was one of the things that helped the case for LIGO, that if you built a LIGO that could reach out to a distance that included 1 million galaxies, then even if the rate for a galaxy like ours was once every million years, if you're sensitive enough to see waves from 1 million galaxies, then you're starting to talk about an event rate that a graduate student could live with. right? And so this idea, these kinds of numbers then helped build a science case for LIGO that there really could be merger sources at a rate that would be interesting for detection. So that's the argument. There must be neutron star binaries today, and of course possibly also mixed systems and black hole binaries. Now these estimates, rate estimates, of course, depended on the existence of these two binary pulsars and maybe a third one that had a short time scale. There are many binary pulsars that will merge on a scale of several ages of the universe. They're just so far apart that it will take them essentially forever to merge. So those aren't very helpful. But at least the two or three that were known with these short time scales then allowed one to make some kinds of estimates of the double neutron star binary rate. These were, But for these systems, black hole neutron star and black hole binaries, it was much more difficult to make rate estimates, simply because we have no observational evidence of either of these things at the time these estimates were being made. All we had were various evolutionary scenarios that took binary systems containing very massive stars, 10, 30, 40 solar masses, orbiting each other. Each star evolves, burns up its nuclear fuel. One star then collapses to form a neutron star. Mass gets transferred from the other star into that. More evolution. This guy collapses to form maybe a neutron star, maybe a black hole. And then you have evolved more and blah, blah, blah. All these are done with complex computer codes, very complicated physics. And those kinds of simulations were used to estimate these rates where we had no direct observational data points. And these rates were then very uncertain, much more uncertain than the rates of neutron star binaries. And of course, in old versions of this view graph, the trouble is we've had to revise all our view graphs now. It's a pain. These people make this discovery. Now we have to change our view graphs. Why couldn't they have waited? And so I could use these view graphs over and over. I used to say the in-spiral of compact binaries is a leading potential source of gravitational waves for interferometers. Well, here I've just added the point, see GW 150914. So we've actually done it, and it was actually one of these systems whose rates were very uncertain, but now we actually have a data point there that helps us to understand how frequently these kinds of things might happen. But the key point is that the merger has to occur, these things damp, and that for the most part, the orbits circularize well before the merger. Okay, any questions? Yeah. Well, it's certainly possible. For neutron star binaries, you certainly expect electromagnetic emission because the neutron stars, as they approach, they're going to tidally disrupt each other. There's going to be collapse. There's going to be lots of nuclear processes, maybe a burst of gamma rays. In fact, the merger of two neutron stars is a leading model for the central engine of the short gamma ray bursts. So you would really like to be able to see a gamma ray burst at the same time as you see a gravitational wave signal from these. Of course, black hole binaries will not emit any kind of direct electromagnetic emission because there are no charges. Except if maybe each black hole is carrying an accretion disk with it. That's probably unlikely because the tidal interaction between the two probably disrupts the accretion disk as the in-spiral. But the whole system could be embedded in some gas, and so the strong curvature of space-time could cause the gas to heat up and emit light. But one expects any electromagnetic signal from this kind of system to be rather weak, but a lot of people are working on that possibility. What kind of signal could you get, and could you detect it with various astronomical telescopes? So it's a very, it's an active area of research, but what you get from this will be much less than what you get from that. Here, of course, it's a mixture. The neutron star will be tidally disrupted before it merges with the black hole, because black hole is like this, neutron star is like a basketball. and that strong gravity is going to really tear that neutron star apart in the final stage, you should get lots of electromagnetic emission there. So, but this is what astrophysicists and relativists are working on today, working out in some best detail they can, and also numerical relativity is playing a big role, trying to work out what kind of signals you get in the electromagnetic spectrum from these kinds of mergers. Yeah. Yeah, okay, so spin is something I've not talked about here at all, but it turns out it's extremely important in many ways. I mean, both in post-Newtonian theory, one of the famous experiments in experimental gravity is the gyroscope experiment of the Stanford Gravity Probe B that measured the frame dragging induced by the rotating Earth. So measuring that kind of spin is very important. In the context of these kinds of systems, spin is extremely important for the kick. When you get a merger, the kicks we saw just from post-Newtonian theory for non-spinning bodies were 175, 200 kilometers per second. Turns out when the bodies are spinning, if they're just spinning in a direction with the spins parallel to the orbital angular momentum axis, you don't get much difference. You get some small differences, but it's not much. It's when you get spins that are strongly misaligned with the orbital angular momentum vector that you get very wild kicks. And people have, these come, of course, out of detailed calculations in numerical relativity, but people have also developed some nice intuition about what's happening. So what's happening is, you know that a spinning object causes drag space-time around with it a little bit. So if you have something with this misaligned spin, let's let this guy have no spin, just to be simple, and this guy has a spin that's perpendicular to the orbital angular momentum axis. Well, this spin wants to drag space-time around with it, so what it does is takes the orbit and flips it up like this. Okay? And then as it evolves, the orbit gets flipped around, and it's like a lever arm that takes the orbit, including the center of mass, and just flings it in some direction that's associated with these spins and this dragging space-time. And it's those cases, and this was discovered with numerical relativity, where you get kicks as high as 4,500 kilometers per second. The huge ones that may, of which that one observation I pointed to might be an example. So spin plays really a crucial role in kicks. It also plays an important role in gravitational wave detection, because if the bodies have spin, and if it's not aligned with well, first if they have spin, that adds terms to the evolution of the frequency of the system. I get back to Blanchet's formula. Or maybe not, there it is. This formula from Luc Blanchet has no spins at all. But if you include spins, there are additional terms at 3/2 post-Newtonian orbit involving spin-orbit coupling, the spins dotted into the angular momentum vector. There are terms at spin squared, spin 1 dot spin 2, and so on, and even higher order spin terms that really affect the evolution of the orbital angular momentum. But also if you have spins that aren't aligned, this dragging of inertial frames kicks in, and it causes the orbital plane to vary. This guy with a misaligned spin is trying to drag space-time around with it, so the orbital plane varies. Well, you're in a fixed direction, so you're going to see a different amplitude of gravitational waves because the orientation of the orbit is changing relative to you. So instead of getting a nice in-spiral waveform like this, with just a nice growing chirp, you get a waveform that is modulated, where the envelope is modulated because the orbital plane is going back and forth and back and forth. And that has very important implications for data analysis, because if you can really measure these modulations, then you start to have a handle on the spins of the two incoming black holes and their orientations. On the other hand, of course, if you do have spins and they're not aligned, it complicates the model tremendously, because you have many, many more parameters to fit, because you have the directions of two spins, plus their magnitudes, plus the mass, and all the other variables that you had before. So the data analysis gets complicated, but the chance of really measuring new effects makes that very interesting. So spin, just not enough time to really go into it here, but spin plays a big role.
So how do we include them? How do we include those terms?
So at P in order, one way to include them is the following. I'll just give one simple example of how spin comes out. In Newtonian theory, there's no spin. Spin has no effect because there's nowhere to put spin in. But here's just one example of how you can get spin. So we have a term, for example, in the equation of motion for body A. It's an integral over body A of rho v squared times the gradient of the Newtonian potential. And let's just take the potential from the exterior, from the other bodies. Okay, so this is integral of rho star. Well, v squared is equal to the velocity of body A plus its own internal velocity squared. This is the velocity of the fluid elements within the body plus the center of mass velocity of body A. And this external potential looks like gm x minus x prime, x minus xb, because we're looking, say, at the potential due to body B, over x minus xb cubed. Well, x we're going to integrate over the body, so we can write this, we can expand this in terms of the x bar, the little vector within the body. So this is xa minus xb plus x bar j dot the gradient with respect to j of mb rab over rab cubed. So I've just done a Taylor expansion of this guy, because I'm writing x is xa plus x bar, small quantity. And of course, you can go to higher orders in this Taylor expansion, but there's a linear term there. Okay? Well, this term is a good term. VA can be brought outside. This can be brought outside. So it's just some term that involves the velocity of body A squared and the potential due to body B and the mass of body A. The first term here gives 0. This is a constant, comes out of the integral, but the integral of rho v bar is 0 because we've defined the center of mass to be VA. So that term disappears. There's the v bar squared term. This is a constant, comes outside. That's the internal kinetic energy, but if we've already discussed, we can combine that with other things. That's the strong equivalence principle stuff that I talked about, so that we know how to take care of that. But now let's go to this term. We have VA squared, we have got an x bar, and everything else is constant, that gives 0. I'll go to the v bar squared term. There's rho v bar squared term times x bar times a constant thing. So that's something integrated purely over body A, but it's a vector, and we use our reflection symmetry to kill it. But there's the cross term that involves VA. VA comes outside, K. We have this stuff, grad J of the external field. Let's call this L, XL grad L, and this is J. So J grad L over that cubed. And then we have the integral over body A of rho star x bar L v bar K d3x. All right? Now this thing you can write as rho star times x L V bar K symmetrized. So it's a symmetric combination, this plus that over 2, plus this X L V K anti-symmetrized. Right? So this is this minus that over 2. So that's clearly equal to that. A little thought will tell you that this is just one time derivative of the quadrupole moment of the source, and if your source is in quasi-stationary equilibrium, that vanishes. But this term, it's the cross product between x and rho v. This is the angular momentum tensor of your body. So it's by carefully taking, now, before we just talked about our bodies as these being like these spherical, point masses, but now if you let your body actually rotate so that it has some net internal velocity circular going around an axis, then you have to really look at these, take care of these terms carefully. And it's especially these kinds of terms that are linear in V and linear in X bar, V bar and X bar, that produce spin terms. And so one piano, you can derive all the spin terms that you need in the equations of motion and the metric, and they agree with what you get from other methods, and so that's a well-defined procedure. But I just, haven't had time to go into it. But it does lead to a lot of important physics that you need to worry about. Other questions? No? No? Well, that, I hope you're following this very carefully. That, my friends, is actually the end of my lectures. So we've covered Newtonian gravity, we've talked about post-Newtonian theory, the basic fundamental formulation, and then we've, post-Minkowskian theory, and then we've talked about post-Newtonian theory in the near zone, and post-Newtonian theory in the far zone, and then next week's lectures, you'll learn a lot about black hole physics from Emanuele Berti, and a lot more about gravitational waves from Sathyaprakash. And so I want to thank you for your attention and for, especially for paying attention to the advertising. Thank you.